All right, hopefully my Apple Pencil doesn't die. As you can see on the side over here with all the slides, fewer slides than last time. Hopefully this video will be a little bit shorter, but thank you guys for powering through. So we are talking about rational exponents today. Yesterday we talked about different types of roots, but now we're going to see what happens when the exponent is a fraction or a rational expression. So here's our definition. If you have a to the 1 over n, so a little fraction, 1 over some number, I can rewrite that as the root of that number. So this is always going to be true. Anytime you have a fractional exponent, I can rewrite it as the nth root of that value, okay? So if you have a to the 1/2, that's the same thing as the square root of a. If you have a to the 1/3, that's the same thing as the cube root of a to the 1/4, on and on and on. These are equivalent ways of writing, okay? And sometimes it's more helpful to use one than the other. So it's good to know how to go back and forth between these two. For some of you, maybe you saw some of the stuff on the PSATs this year. The PSATs and the SATs love exponent stuff. So maybe it didn't show up a ton on this year's one. I'm not totally sure. But like these are like wonderful for whoever writes the SATs. So if you guys can get this section locked down, that's going to be super helpful for you on those tests. All right, example 1. Use radical notation to write the following, or to rewrite the following. Simplify if possible. So 81 to the 1/4, all right, our notation would say that would be the same as the 4th root of 81. Can I simplify that? Is there some number that when multiplied by itself 4 times equals 81? Well, I could rewrite this as 3 to the 4th, right? 3 times 3, 9, times 3, 27, times 3, 81. So our answer here, our simplified answer would just be 3. All right, this next one, parentheses are super helpful, okay? So this whole thing here is one term. So I'm going to rewrite this as the 5th root of 32x to the 10th. Okay, well, I can think about these because these are multiplied here, 32 times x to the 10th. I can start by thinking, well, what's the 5th root of 32? Maybe you already know the answer to that. I can rewrite this actually. 32 is the same as 2 to the 5th. And then I have x to the 10th over here, okay? So I can simplify this. Well, the 5th root of 2 to the 5th is just 2. And the 5th root of x to the 10th, again, what times itself, x to the what times 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 x to the what equals x to the 10th, x squared would do that. All right, last one. Cube root of 16x to the 7th. All right, this one's going to be a little different. 16 is the same as 2 to the 4th. So I'm going to rewrite that. 2 to the 4th, x to the 7th. What I then want to do is I kind of want to break these apart, and I want to say, well, okay, 2 to the 4th, I can't do much with that, but 2 to the 3rd, I could do something with that. So I'm going to actually split this up, and I'm going to rewrite this as the cube root of 2 to the 3rd, and then I want x to the power of some multiple of 3. My highest multiple of 3, that's less than 7, is 6. So cube root of x to the 3rd, cube root of, 2 to the 3rd times x to the 6th times, what am I left over with? Cube root of 2x over there, okay? How could you simplify this first bit? Well, the cube root of 2 cubed is just 2, and the cube root of x to the 6th is x squared, right? X squared times x squared times x squared equals x to the 6th. And then I'm left with the cube root of 2x. And folks, that's long and clunky, but that is your answer. All right, so I could simplify and have some numbers be free from that radical sign, some x's be free from that radical sign, but not all of them, because 4 and 7 are not multiples of 3. They're not multiples of that root, okay? Our next rule is going to help us even more. We've been doing this kind of without realizing we've been doing this. Our next rule is the definition of Oh, this should not be a 1. This would be an m over n. So if m and n are positive integers greater than 1, with m over n in lowest terms, so they're just saying, like, if you had, 9 over 3, you could simplify that to 3 over 1, I can rewrite this in 2 different ways. This first one is kind of similar to the 1 over n, right? The n, your denominator, that is your root. And before, if I had a to the 1 over n, it's kind of the same as the nth root of a to the first, but we would never write a to the first. I would just have a. So the main thing to take away here is your numerator, that just sticks with that base, a to the m. Your denominator, that's the thing that's going to go outside with the radical sign. The other way that you can write it, though, would be like this. I still have that n as my square root, but now the m is outside that whole entire thing. So you can either, raise it to a power first and then take the square root, or you can take the square root and then raise it to a power. All right, 2 different ways of writing the same thing, as long as this, of course, is a real number. So we just have to be a little mindful. Is a negative and is n even, then we won't have a real number. Let's do some stuff with this. I would like to rewrite and simplify. So I have 9 to the 3 over 2. That 3 is going to stick with the 9, so 9 cubed. That 2 is going to go outside with the radical sign, except we don't usually write the 2's out there, so it's just the square root. I don't like this version as much, though. That seems complicated and annoying. Let's actually use the other method, square root of 9, and let's raise that to the third. Oh, square root of 9, that's just 3, right? So I'm just replacing square root of 9 with 3. What's 3 cubed? 27, all right? So usually this is my go-to form to write things, like the go-to form to rewrite things, but sometimes this other form is a much more helpful form. So it's good for you guys to know both of these. What about this next one? I have negative 8 to the 4 over 3. Well, you could write this in 2 different ways here. But because 8 is a perfect cube, I think I want to deal with the cube first, okay? I'm going to leave this negative sign out front, and I'll explain that a little bit more in a second. I'm going to rewrite this like this. Negative cube root of 8 to the 4th power. Cube root of 8 is what? Okay, you said 2. Nice. 2 to the 4th power is what? You said 16. Awesome. Great. So my answer here is negative 16. So why did I take that negative out? That seems a little weird. Well, if you're mixing even and odd exponents and roots, or powers and roots, then I want to be careful with my negative signs here. So negative 16, let's start with that. Let's work our way backwards. If I were to take the 4th root of negative 16, well, that wouldn't work, right? That isn't not gonna get me anywhere. I can't take an even root of a negative number, right? But if I just said, hey, negative, and then what's the 4th root of 16? Well, that would give you negative 2, right? Negative 2 cubed, what would that give you? Well, that would give you negative 8, right? Negative 2 cubed would give you negative 8. So when you are raising to an even power and then taking an odd root and you see this negative, I can leave that negative out front. For all of these problems, like when in doubt, try to go the reverse direction and see if you can get the proper sign. If you can get the proper sign, then good job, you did it. Okay, what about this last one? That 3 in the denominator, that's going to go outside with the root, and then I have 3x plus 7 to the 7th. It might seem at first like I can't do anything here, but because that 7 is larger than this 3, I can actually rewrite this. So 3x plus 7 to the 7th, I could split into 3x plus 7 to the 6th times 3x plus 7, and I'm allowed to separate 2 terms that are under the same radical sign, okay? So I can split this into the cube root of 3x plus 7 to the 6th times the cube root of 3x plus 7. how could I rewrite this first term? Well, here's where we've been doing this secretly all along. I'm going to use that rule. I'm going to go in reverse. 3x plus 7 to the 6th over 3 times the cube root of 3x plus 7. What is 6 over 3? Hopefully someone said 2. This thing right here, that whole expression just turns into 3x plus 7 squared times the cube root of 3x plus 7. Guys, that one's a little funkier. So we've kind of been doing this little trick all along. When you have some root like this underneath your radical sign and you have some larger than just 2 root outside, we've been trying to think, okay, what times itself 2 more times is going to equal 6? This is so much easier. Just rewrite it as a fraction and simplify it, okay? Anytime you see something like that, you know, if I have the square root of, oh crap, now I need to come up with an example on the spot. I didn't think that through. If I have the square root of, let's say, x to the 7th. Okay, I like this one. You can always rewrite that as x to the 7 over 2. Okay, that didn't really help me simplify this too much. We would actually have to use a process similar to what we used for this problem. So I'm going to choose a different example. What if I had the square root of x to the 16th? Okay, I can use this new rule and rewrite this as square root raised to the power x raised to the power of 16 over 2. And that just equals x to the 8th. Okay, I love this rule. This helps us simplify things so much easier than trying to just like think it through the long way. Okay, so that again was just a random example. Your final answer for this problem is what is in that rectangle right there. Okay. If you are raised to a negative m over n power, you guys have dealt with negatives before, right? A raised to a negative... I'm going to use a j over here, is the same as 1 over a to the positive j, right? So here, I'm just saying, hey, my fraction's negative, drop that thing down to the denominator. As long as this is not 0. I cannot have a 0 in the denominator, right? Okay, let's keep going. Write each expression with a positive exponent and then simplify. So I first want to drop this whole term to my denominator. And then which way do you think would be the best to rewrite this thing? Should I do the cube root of 64 squared or 64 squared and then take the cube root? I think it might be a little bit easier to do the cube root of 64. That is a perfect square, a perfect cube, pardon. So the cube root of 64, and then I'm going to square that. What is the cube root of 64? Hopefully you said 4. It is 4. And then what's 4 squared? Hopefully you said 16. That's exactly what we're looking for here, okay? Again, if it's going to take us a little more time to try to get some of our perfect cubes, you know, memorized, that's okay. We are practicing, right? That's what we're doing. All right, for this next one, I have negative 16 in parentheses here over raised to the power of negative 5 over 4. So I'm going to rewrite this as 1 over negative 16 to the negative 5 over 4. Now, because I have mixed numbers here, that should not be negative. Hopefully you guys caught me on that one. Positive 5 over 4. Because I have mixed numbers, 5 is odd and 4 is even. I'm going to be taking an even root of this and then raising it to an odd power. So I am allowed to rewrite this as 1 over negative 16 to the 5 over 4, okay? Again, this is only because I have an odd number in there. 5 is odd, which means that negative can kind of stay outside. Okay, what is, let's rewrite this again. What is the 4th root of 16? We're going to start there, and then we will raise it to the power of 5. Hopefully, the 4th root of 16, hopefully you said that would be 2. So right now I have 1 over negative 2 to the 5th. That negative is not inside these parentheses now. So what's just positive 2 to the 5th? 2 times 2 times 2 times 2 times 2 is going to give us 32. So right now I'm dealing with negative 1 over 32. That's the answer we're looking for here. All right. Again, if you want to, you can check yourself and make sure that we are getting what we're supposed to be getting by kind of doing the reverse process. You could say, hey, what is the fifth root of negative 1 over 32? That would give you negative 1 over 2. And then if you were to raise that to a power of 4, that will end up giving you your negative 16 back. Okay, so again, because we have the negative included here and because I have a mixture of odd and even, I want to pull that negative out and just deal with 16 to the 5 over 4 or 1 over 16 to the 5 over 4 and then kind of tack that negative back in at the very end. That's only because I'm mixing my odd and even numbers in my power. Example 4. We are continuing on. Okay, you guys know these rules already. If I'm multiplying something with the same base, what do I do with these two exponents? 2 over 3 and 7 over 3. Well, if I'm multiplying with the same base, I'm adding those. So this is going to turn into b to the 2 over 3 plus 7 over 3. What is 2 over 3 plus 7 over 3? Well, it's 9 over 3. Oh, I can simplify that. This is just going to be b to the third. Keep going here. X to the 1/4 times x to the 1/2. I would need to add those. So 1/4 plus 1/2, what would that be? Maybe you said 3/4. X to the 3/4. Awesome. I can't really simplify that anymore. So that's as far as I can go. Okay, this one over here. What's the rule when I am dividing and I have bases with I have the same base? I would want to subtract. So 5 to the 1/3 minus 7/3 is going to be 5 to the negative 6/3. 6 over 3 is 2, so 5 to the negative 2. But they said write results with only positive exponents, so I need to use my negative exponent rule and rewrite that as 1 over 5 squared. 5 squared is just going to be 25, so 1 over 25. So you guys used a lot of these exponent rules a couple weeks ago. Those are coming back. Now we're just tacking on some new stuff with fractions, with negatives, with different types of roots. And it gets more exciting. All right, what's our rule if I am raising something to a power and then raising that whole thing to another power? What do I do with those two exponents? Yeah, I would want to multiply them. So 1/5 times 3 is going to be 3/5. 2/3 times 3 is going to just be 2. Okay, this first term I would like to rewrite. I think I would like to figure out the fifth root of 32 first because I think that'll work out nicely. So fifth root of 32, and then I'm going to want to cube that times x squared. Well, the fifth root of 32 is just going to be 2. So I have 2 to the third x squared. What's 2 to the third? Cool. You said 8. Awesome. Our answer is 8x squared. And that's what we got to do. All right. Let's keep moving on with this other one. So up top, I have 2 base a terms multiplied. So I would need to add those. So I have a to the 1/4 plus negative 1/2. What would that end up giving us? We said a to the negative 1/4. Awesome. Okay, good. That all is being divided by a to the 2/3. How should I handle this? Okay, I need to subtract. So I have a to the negative 1/4 minus 2/3. I need a common denominator over here, so I'm going to just quick take a little sidebar. This would be negative 3 over 12 minus, I would multiply this one by 4 over 4 to get a common denominator of 12. So minus 8 over 12, that's going to give me negative 11 over 12. Okay, so we are rocking with a to the negative 11 over 12. Again, I only want positive exponents, so that's going to be 1 over a to the 11 over 12. Okay, so combining old rules and new rules, cool. Okay, I was kind of talking about this earlier, right? We've been secretly using these rules without really knowing it. I can also rewrite the other direction, okay? So the 10th root of x to the 5th, I can rewrite as a fractional exponent, 5 over 10, 5 over 10. I can simplify that to 1/2. And then 1/2, I could actually rewrite that as a square root. So our final answer here is the square root of x. That's what we're looking for. And we are assuming that variables just represent positive numbers here, so I can just leave that as the positive square root of x. Square root of 36, well, that's the same thing as 36 to the 1/6. Here, we want to use rational exponents to simplify. If I'm looking at the 6th root, right, I know the square root of 36, that's cool, but the 6th root, I'm not so sure about that one, but I might be able to rewrite it with a smaller index number. That's what we're going to try to do for this problem here. So I know that I could rewrite 36 as 6 squared, and then I'm raising that to the 1/6. Okay, well, I know that if I'm raising to a power, then raising to another power, I would multiply those. So 6 to the 2/6. I can simplify that and get 6 to the 1/3, which I can rewrite as the cube root of 6, okay? So for this one, we're just rewriting it. I'm simplifying it by decreasing this index value. Instead of 6 and 36, I was able to simplify by making both of those numbers smaller, just 3 outside on my radical sign and 6 on the inside. Okay, so I rewrote this as a fractional exponent, rewrote my perfect square as something squared, and then used some of my other rules here to simplify. We have one example left, folks. Example 7. I would like to write this as a single radical. When I'm multiplying, I can't multiply two completely different roots together. So here I have a cube root and I have a square root. I can't just multiply the numbers under there. I need them to kind of match in some way, shape, or form. Okay, so I'm going to start by just rewriting these as fractional exponents. 5 to the 1/3 times 2 to the 1/2. Okay. If I want to be able to multiply these, like I want to find some way to gain common ground here. Well, 1/3 and 1/2, I guess I could figure out a way to write those both with the same denominator. If I can write them both with the same denominator, then that means I could combine them under a radical sign, okay? They want us to write this as a single radical, and I know that my denominators here are connected with the number that goes on the radical, with the root, okay? So I'm going to rewrite 1/3 as 2/6, and I'm going to rewrite 2 as 3/6. Stay with me here, all right? I'm going to rewrite all of this. I should really be putting equals equals. I'm going to rewrite this as 5 squared times 2 cubed to the 1/6 power. I think the easiest way to think this through is in reverse. Okay, I could go from this step to this step pretty easily. We've done that a lot in the past. And then raising 5 to the power of 2 and then raising that whole thing to the power of 1/6, you know that you just multiply 2 and 1/6, right? So I think it's a little easier to see this kind of in reverse. But now we're going to have to start thinking about it from both directions, okay? So up here, I had two completely different roots. My process from, now I just have arrows everywhere. My process from here to here was, okay, I know my denominators have something to do with roots, have something to do with radical signs. So how could I rewrite these with the same denominator? Okay, 3 and 2, I could both rewrite those with a denominator of 6. And then 2/6 is the same as 2 times 1/6. 3/6 is the same as 3 times 1/6. So I could rewrite this as a fractional exponent. What is 5 squared? What is 2 cubed? What is 25 times 8? Our final answer for this thing is the 6th root of 200. That's what we're looking for here, okay? So that is written as a single radical. I'm going to say this one more time. I cannot just multiply things that have different numbers outside the radical, different roots. What I need to do is I need to find common ground here. The way that we did that was by saying, hey, denominators are connected with roots. How can I write these fractional exponents with the same denominator? And then it's not quite factoring out, so I don't want to use that term, but it's a similar process to factoring out. Rewrite those fractional exponents as, an integer times a fraction. And then I could simplify just those numbers, those powers, 5 squared, 2 cubed. And I could finally rewrite that fractional exponent 1/6 as a 6th root. Congratulations, folks, you're done with this video.